Alright, so let f be a function defined on the closed interval from 0 to 7. The graph of f is shown. Let g be a function that depends on that f function, on the area under the curve. G of 4. Alright, so most important here is this number 2 right here, because that tells you when do you start accumulating, from there. So starting here on the area. So if we do go from 2 to 4, G of 4 would be 2, 2x is 4. 2 to 4. And you just find the area under here, no? This area here, which is 4 times 2, 8, 4, so it's going to be 4. G of 6, that's going to be as we continue on. So we went forward, then we go back. That's going to be 4, 2 times, so it's going to be 1. No? 2 times 1 is 2 divided by 1. 3, so the answer would be 3 because we went forward, 4, then came back 1. So the net distance from from that 2 is 3. No? Is it? G of 0. G of 0. G of 0. How do we do G of 0? See, we're right here. Again. So right here. And we're going to go and do the integral from what? From 2 to 0. What do you guys think the answer to this is? Anybody? What do you guys think the answer is? 4. 4? Like with physics, if in any way I can tell you, like with physics, look, if we started here, and this was actually 0, okay, let's just go, this, we started here and this is 0, and so we go, x is 2, and if you go to the right, and this is on top, that's because it's going to be positive. So if I go from here and go to the right, that's going to be positive. Positive what? 4. Positive 4. But if we go here and we go that way in that direction of that one is go to the left, it's gonna be a negative. This becomes negative if we go to the left. So everything switches. So if we go here and then let's say it goes like this. So in this one is that this one's gonna be negative 4. If we go this way, this would be negative 4, and this would become positive. So everything switches with the direction because the direction is so important here. But when we go forward, you see it that if we go this way, this is positive, negative, positive. But if we go backwards, just make sure to put a negative in front of it, or everything switches. So it would be, if we go here, if we do start here, and we go this way, what's the answer then? 2, 0. Negative 4? Negative 4? Yeah. Well, here, look. There's a property of this thing. There's a property that we're going to go over the properties like next week. So I don't know when. If it's going from 2 to 0, which it's telling you going backwards, you could do this. It's called the you put a negative in front of it and switch the bounds. So basically, if you just go, no, this would become negative and change the bounds. Just flip the bounds. And then you can go f of t dt. Okay, f of t dt. Okay, well, if you look at it this way, then we are looking at 0 to 2, f of t dt. So we are looking from 0 to 2, which is positive, but then we put the negative, becomes negative 4, just by looking at the property of it in another way. No? We'll go over that properties later. All right. Here we go. Get a ruler if you need to, and copy this down. This is basically going back to the basic when they started thinking about what is the area under a curve. So we're going to the very beginning and how people used to do it, maybe thousands of years before, 500 years ago. Estimate the area of the region S, bounded by the graph y equals x squared, the x-axis, and the lines x equal to 0 and x equal to 1. So we want to know, and that's the one I had. That's how we started chapter 6, where I said the second big question is to find what is the exact area under a curve. No, so what is that exact area under that curve? And so what is this area here? No. And I told you that maybe you can look at it like this. You can look at it that, well, this is supposed to be a square again, but it looks like a rectangle because the height of one and a height of one and a length of one. So the whole thing looks to be 1, no? Because base times height and it's a square. So it would have been a 1 here, no? So it's this thing is it's supposed to be a square. It's 1, and if you think about it, then if you cut it in half, this square, and go like this, and go diagonal like that, two triangles, maybe this would be less than 50, because this could be maybe 50. Thinking about it, and then you're counting this, that it's not part of it. So maybe 0.4, maybe something like that is this area. All right. So how did they proceed in thinking about this to find what exactly it is? What if instead we would have done these rectangles, no? And I would have said, you know what, it's going from 0 to 1. Let's make 2 rectangles, no? So 0.5. This is 0.5. So I'll make a rectangle where it's the right side of rectangle goes like this, and I make a rectangle here, and then I go here. I make 1 rectangle, and then I go back to our actual graph x squared and make another rectangle. So I got 2 rectangles, and add up the areas of because we know what area rectangles are, base times height. Base times the height. So I would be saying that add this up, add it to this would be a better approximation for the area. But then I'm counting this part that it's not part of it, and this is not part of it. So it's still not good. What if I continue on and let's do 5. So the idea is that you do a bunch of them. So we're gonna make rectangles that are gonna be standing up rectangles so let's say it's 5. So what would be the width if it is 5 rectangles that I want to draw here? It's going from 0 to 1. So from 0 to 1. And I want to cut the 0 to 1 into 5 intervals. What would it be? 0.2. Yeah, it's 0.2. 0.2, and that's, so it's 0.2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So what I'm gonna do then, what we're gonna do, and that's what we're gonna do here, is gonna be let's call 0 is 8, the first where we start A to B, and we're just gonna go 1 minus 0 divided by. I want to have 5 rectangles. I had to 2 first. I did 2. Let's do 5. It's arbitrary. No, it's better, the more there are, the better, no? So I'm saying b minus a divided by n subintervals, no? The n numbers, n can be, I said 5, we want to do 5 right now, it could be 10, it could, the more the better. 100, 1,000, like that. So let's just do it for right now. We're going to say that it is going to be, b is 1 minus 0, n is 5, which is 0.2. 0.2. So the width is going to be 0.2, and it's going to be right. It's on the right. This is called a Riemann sum, and it's a right Riemann sum because I want to do where the height is on the right side, not on the left. So I'm starting here, so I'm going to go like this, and go, that's my rectangle, it's an over, again, that's extra, that's this part here, but whatever, so it's getting closer, and then closer, so here, and like that, no? Let's see. And then here on the graph, on the x squared, and like this. And then yeah, here there is one here that we can do this. And the idea is that if you add these up, 1, 2, 3, 4, 5, it's gonna be getting closer to what it is. And let's do it. Let's go ahead and find it, no? So it's called the right Riemann sum. Of 5 sub n. So it's r sub n. N is the number of rectangles, no? And we're doing 5 in this particular what we're doing here. If this was 10, then you say a right 10, a right 100, or whatever. And that will equal to a right Riemann sum of 5 subintervals will equal to the base times the height. Well, we equal to, I don't know if you guys, the summation formula, there's a summation formula going like this. The sum of 5, 1, 2, 3, 4, 5. So from I equal to 1, from the first rectangle, all the way to the nth rectangle, and the nth rectangle is the 5th rectangle, of the base times the height. The height is going to be, this is the height of it, this is the height for this one, this is the height for this one, this is the height for this one, and this is the height for this one, this is the height for this one. The height is the y value of x squared. That's what we're doing, x squared of y. So we're going to do what? F of xi times changing x. Well, we already, this is called changing x. This what we did is the changing x is actual width of it, no? This is called change of x. B minus a divided by n, which we did, it was 0.2. This is the change in x. So, change in x. If I'm going to keep all variables, I could, I've already told you that we're doing 5, but if it wasn't, it'll be the nth, how many cuts we got, no? How many rectangles we want. So if I just want to have it as a formula, let's do it like this. It's more, not, it's a formula, R n, where that's a variable on how many you want. It could be 5, it could be 10, it could be 100, it could be 1,000. N is arbitrary to how exact you want to be. And then the base times the height. And the sum, the summation of these things. That's what this means. Okay, now, Let's actually apply it to 5, R5, no? Let's go, R5. So this is the formula, and then now this use it. R5 equals to the summation. Can't even write a summation from I equal to 1 to 5. What is the function we're dealing with, working with here? What function are we dealing with? What function are we dealing with? X squared? Xi squared times the change in x is what? 0.2. So that 0.2 is constant because we gotta keep it the same width for all of them. So the width for all of them is the same. What can we do here? I'm going to factor out that 0.2. See, what we're doing here is because we're going to multiply the base times the height added to 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 the height. So this is a constant. Let me bring it out. 0.2. And let me, let's go like this. Let's start from the right. Oh, we can go from the left. It doesn't matter. We're getting this height and then plus this height, plus this height, plus this height, plus this height. What's the height of point? Because this is 0.2, no? This is 0.2, 0.4, 0.6, 0.8, oh, it's 1. It's 1. So 0.2, you're going to square it, no? Because that'll give you the height here, yes, doesn't it? It's the y value of x squared, no? Yes? So what is 0.2 squared? That's what's going to go here. 0.4 squared. And so let's go. It's going to be 0.2 squared plus 0.4 squared plus 0.6 squared plus 0.8 squared plus 1 squared. Get a calculator to do this faster. Go ahead and put all this stuff in the calculator. That's what we're going to do. So it turns out to be calculate 0.2 in, and then I'm going to do brackets or parentheses. Where is parentheses? Okay. 0.2 times 0.2 squared. It's positive, so 0.2 squared plus inside 0.4 squared plus 0.6 squared. It's right there. Go get your calculator right there. 0.6 squared plus 0.8 squared plus 1 squared. All right. What are we getting? Okay, I got it. What are y'all getting? 0.44. 0.44. That's basically like the idea here. So why don't we do it like that? Look. I just thought about it. Let's do it for 1,000. How the heck are we going to do it for 1,000 and put it in a calculator though? If we do 1,000, it's going to be like the whole day. If I go, this is not even going to do it justice. No, because it's not even that much. This is not even 1,000. Yeah, I don't know. That's not possible, man. But you kind of get the idea here. That's not even 1,000. Huh? This is not even. All right. But you see it now, no? That it's getting closer to what it is, no? To what it would be, no? And then, well, this is how many? We'll count them right now, no? Whatever. I'm just I don't know. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. That already looks really good. Dude, 1,000 would be really, really, really close. So this is called now. All right, let's go. The actual one would be the limit, as in, okay, so there's the formula. The limit. So now this is how area and derivatives are related. Is the limit as n goes to what? The number of rectangles goes to infinity. You got an infinite, not even 1,000, which is, I can't even draw, it'll take a whole day. Imagine a billion, a gazillion, then it'll give you exactly it. So the limit as n approaches infinity of the sum from I equal to 1, starting with 2, summing up the first rectangle, all the way to the end of f of xi times that change of x. So there's that. F of 1 times 0.2. F of 0.2 times that. I did it slightly different in what I already did, but it's the same. The reason why I just, because they all are being multiplied by 0.2, 0.2, I just factored it out. But it's the same, it'll give you the same answer that you got. You worked it out, it is tedious, it's 0.44, right in Riemann sum n, which is 5, blah, 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 R5 is blah, 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 blah. Okay, there's a left Riemann sum 2, that instead of doing a right 5, we could do a left 5. So if we do cut it into 0.2, 0.2, or whatever it was, 0.2, then we start on the left instead of the right. So I start here, well, I'm not even getting, because that's 0. F of 0 is 0. So I'm not even making a rectangle here. So it will be, this one right here was it, what was it, under or overestimate? It's an overestimate, no? Because I'm counting this little part, this is an overestimate of what it is. Whereas in this one, it will be an underestimate, because then I go here, and I make one here, and then I go here, and then I go here, make another one, then go there, there, and then there. It'll be an underestimate. That's it should be counted, but it's not there. I'm using this part here. I'm using this as my height. I'm using this as my height. And so I'm missing that part, this part, this part. So it's an underestimate here. When it's an increasing and I'm making a left Riemann sum. So it will be a left 5 Riemann sum will be, the width is the same. So let me factor out 0.2 times f of 0, 0 squared plus 0.2 squared plus 0.4 squared plus 0.6 squared plus 0.8 squared. We're not doing this because, again, we're doing this as my height. So it goes like that. So it'll be 0.2, then we'll multiply it by this thing. Let's put it in the calculator. 0 squared plus 0.2 squared plus 0.4 squared. 0 squared is, don't even put that in it. Well, write it down, but that's not going to go in the calculator. Because what else is it going to be? So 0.2 times quantity, 0.2 squared, 0.4 squared, 0.6 squared, 0.8 squared. What is that? Point 2 times the quantity, 0.2 times the quantity, 0.2 squared, 0.2 squared plus 0.4 squared plus 0.6 squared plus delete squared plus 0.8 squared. What are you getting? 0.24. This is a underestimate. And you would think that the answer would be, now we're like getting it in between. It's going to be definitely the area under there will be between 0.44 and 0.24. Why don't you what's 0.44 plus 0.24 divided by 2? Let's average it out. Let's just say the average of the over and the under. What is that? 0.44 plus 0.24 divided by 2. What is it? 0.34? It's getting close. The answer is 0.3333. It's 1/3 the answer. The exact answer. All right, let's go. Number 1. How would they test you on your understanding of Riemann sums? They'll do this. F of t is a continuous function from 0 to 12, where f of t is the rate that Catherine travels from her home to school, which is the velocity. F of t is in miles per minute, and t is in minutes. What is the total distance that Catherine travels? Yeah. Depending on what yeah. This is it needs more direction, no? It says, well, what do you want me to do? You want me to do a left Riemann sum or a right Riemann sum? So we could do a right Riemann sum, and we could do a left Riemann sum. 10, 14, 20, so it's not a strictly increasing function. It's not. So because it's going from 10 to 14, 14 to 20, then it goes down, then it goes up, and then goes down. Yeah, all right. What else? Let's go. So let's do a right 5. I think that's what. So this doesn't have directions. It has to be exact. What do you want me to do? Left Riemann sum or right? Let's do a right Riemann sum, and we're gonna go right. Let's go with right. A right 5 Riemann sum. Is it 5? 1 height, 2, 3, 4, 5. Yes. Is the change in x constant or not constant? Are is the width of the rectangles constant? Yes or no? Isn't the input t, this is t and this is the velocity? So isn't it going 0 to 2? Is 2 to, oh, it's not. I thought it was. It's not. So you can't factor it, no? It's not. 2 and then 4, then 2, then 2, then 2. Messing it up. Because I wanted to factor it out, and so it'd be easier, but we can't. So we do have to do the width times the height, which you don't even have to calculate, no? The width, base times the height. Well, the base is going to be 2 times what? The height of this is what? If I'm doing a right 5, which should it be? 10 or 14? 14, because it's on the right. These are the outputs, no? Of F. So 14. If we do, then we're gonna do plus what? 4, no? This is 4, the width, times 20. Two plus 2 times 2 times 15. 2 times 30. and 2 times 20. 28 plus 80 plus 30 plus 60 plus 40. How much is that? 138, 238? Yeah. So what are the dimensions of this? If this is 238, what is it? 238 what? Miles. So this is the distance it traveled. So if we did a left Riemann sum, we probably we would definitely get a different answer. But these are approximations. Oh, you got a pen? Oh, it's already done? Where? Where? There you go. Oh. Okay, so there's these other kind of approximations, and it's just like whatever. It's instead of doing a left Riemann sum, we do a midpoint approximation. And what does that mean? That the midpoint approximation, well, that the height of the rectangles is not left or right, it's in the middle. So the middle of 0.2 is 0.1. So this would be the height, and then going like this. So I don't know. I just kind of have to teach this, but it's kind of like whatever. Then 2 to 4, we're gonna go to the middle instead, and then go like this. Yeah, whatever. Like, and from 4 go the middle of not to get to the height. The height changes. That's the only thing. So it's gonna go here all the way like that, the rectangle, and then the middle of this, and then the middle of this, and then make those. So it's an over approximation, I think, because of this. It's just whatever, no? So that's going to be in the middle, and it's kind of tedious to be doing it. All of this kind of whatever. Blah 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 blah, and then the answer, and then that's going to give you 0.33, which this one gives you the correct answer. Not always. It just kind of luckily got the answer exact, but. That's the idea. I'm like that's the midpoint where the height, the big one is at the height of the rectangle. Where is it at? And with the midpoint, you got to go to the middle and then get to the graph. Let's go number 2. So I don't know. Let's go ahead and copy down number 2 down. So, like I would be saying with my Algebra 2 classes about pi. Pi is world famous, gets all the, like, it's like, you know, everybody knows pi. But the letter E, the constant E, is it should get more recognition, but it doesn't. And it kind of like in calculus, the derivative and the integrals get all, well, that's what they are, they get all the credit. But the engine and the main thing that drives them both is the idea of the limit. The limit is, because of the limit, everything is what it is. Suppose, let's go to number 2. Selected values of f of x over the interval from 2 to 38 that are given in the table. Okay. Suppose this table is used to compute a midpoint Riemann sum for f over the interval from 2 to 38. using as many subintervals as possible, what is the value of this midpoint sum? So what would be the midpoint sum? I mean, how would you know which one to do? Midpoint is in the middle of 2. So well, let me see if we can graph this. You got 2 and 7, so you got 1, 2, 1, 2, 3, 4, 5, 6, 7. There's a point there. You got 8 somewhere over here, and then it's 9. I don't know, and don't do this. You don't have to do this. 18 is 14. So these points, and we don't even know what the graph's doing, but we got those points. So when you got like that, and you got this, and this is going to be your midpoint one. You're going to go like this with it. So this one's going to be the midpoint that we're going to use for the height. So it's going to be this. Okay, so how are we going to use this? It's going to be the M5. Oh, how many? How many are we going to be able to use? Right here in the middle, 1, and then 2, 3. So M3 is going to equal to the height times the width. And I said it was something like that. What's the width of this thing here that I had drawn? This is the midpoint. What is it? 12? 12. And then the height is what? Yeah? So then this is going to be, M3 would be the width, or whatever you want to do. If this is the one we're going to use, that's the height is 9. I guess we can go the height, base times the height. Well, the width is 12 times the height. 12 times 9? 12 times 9, so it goes like that. 14 minus 2 times it by the height here. So you can go like this. You go skip it and go like that. So we go like this, and like this. What am I doing? We go like that. So this be so 12 times 9, then what? 12 again? Whoa. It is. It's a constant, huh? It's constant, huh? We could factor it out, no? And just go what? 12 times what? Each height, is it? Because it is 12. It's 12 and it's 12. So 12 times the height. What is this? 9 and what? Plus what? 20 plus what? 10? 39 times 12? What's 39 times 12? And there's the trapezoidal sum. Trapezoidal sum is actually the average of a left Riemann sum with the right Riemann sum, and the formula would be what would be trapezoidal T n. Let's do it for this already. What would it be? T5. Would it be T5 trapezoidal? I think it's T5 would be. If we do it for T5, we do it like that. So it would be the width of the rectangles, because these are the trapezoids. Look, trapezoid. What are trapezoids? Trapezoids go like this, no? Trapezoid. If I go here, I go here. A trapezoid goes like this, no? That's a trapezoid. Remember? That's a trapezoid when we started. We did the homework. Like that. It's a trapezoid. And then, what is it? 1, 2, 3, 4. And then I guess we go here to here. So that's the trapezoid. So the width is 0.2 still. 0.2. It's constant. The height is going to be what? What's the height? The height is, wasn't it? What was it? How did we come up? The base is at the height's added, wasn't it? Or whatever, B1 or H1 plus H2 or whatever. So it would be what? 0 plus what? 0.2 divided by 2? Wasn't it? And it would be what? 0.2 plus what? Divided by 2. You get them all, whatever. So that's kind of like what it is as the idea of this one. 0.322 is the answer when we do it this way. Okay, finish it off. A right Riemann sum on a strictly increasing function is it's increasing. I guess this, even though it's concave down, but it's increasing. Concave down, increasing. And we do a right Riemann sum. If we do a right Riemann sum, is that an under or an overestimate? Overestimate. A left Riemann sum on a strictly increasing function is a what? A left Riemann sum. So we do a left. It would be what? Underestimate. A left Riemann sum on a strictly decreasing function, a left Riemann sum on a strictly decreasing function would be a overestimate. And a right Riemann sum on a strictly decreasing function, an underestimate. And we are done for today.